In physics, we are interested in studying nature at the most general level. Now, the knowledge generated by physics has proven absolutely critical for many of the technological wonders of our modern world. For example, the theory of quantum mechanics has proven extremely fundamental for the invention of the transistor and ultimately the modern digital computer. Here at NTU Physics, we are continuing to push forward the frontiers of physics research in many areas. My colleagues are going to tell you about the exciting research that they are doing. Let's take a look.
This year is probably one of the coolest labs in Singapore. I mean literally. Here, we are cooling down atoms to almost absolute 0 Kelvin, with roughly 273 degrees Celsius minus. Fun fact, at these temperatures, the behavior of atoms is just governed by quantum mechanics. They do not behave like billiard balls, like classical billiard balls, but more like theta waves. And this is very interesting. We can prepare exotic states, quantum states like superpositions or entanglement, which is actually not possible with any classical systems. In future, we envision to make computers which uses these quantum mechanical properties and harness it, like the superposition states or these entanglements, to perform certain types of calculations which are not possible to do on a classical computer.
Electrodynamics is the branch of physics that governs the behavior of light and other electromagnetic waves. In this laboratory over here, we design new types of materials in such a way that they can bend the light around an object, just like water streamed around an object. So this can render this object invisible. One of the very cool and almost sci-fi-like applications is to make so-called invisibility cloaks out of these materials. In this room, we are testing out our design of such materials.
In electronics, we control the flow of electrons to make transistors, memories, and all other devices found in our modern-day gadgets. In photonics, we manipulate and control the flow of light, or photons instead. This can speed up the various processes to transmit and process information and can be much more energy efficient. To control light with wavelengths in the hundreds of nanometer length scale, we use nanotechnologies, a research domain called nanophotonics. In this clean room, we create many different intricate nanostructures to guide and control the photons.
Presently, silicon solar cells are the most common solar cells around us. Silicon solar cells, however, suffer from one key limitation. It costs a lot of energy to purify silicon. Now, new generation solar cell materials that uses low-temperature solution-based methods will address this key limitation. My research uses very fast lasers that operate at 100 billion times faster than a camera flash to track and monitor how electric charges move in these new materials. Now, understanding the physics behind how these electric charges move and how the current can be transported efficiently will allow me to work with chemists and material scientists to design and fabricate cheaper and better materials than silicon.
You might think that physics only applies to electrons and protons, metals and insulators. Well, I have a surprise for you. Physics actually also applies to economics and social phenomena. I am a theoretical physicist here at NTU, and I specialize in econophysics, which is the physics of stock markets and economies. And I specialize in studying market crashes, and recently I've started looking into early warning signals for market crashes.